So I'll do an example here of how we can solve this system of equations here. So here we go. Okay, so we have this equation here. X prime is ax, all right? And this time, when we go ahead and find the characteristic polynomial here, we realize that there's only one solution. Okay, so we need to, just as in the earlier studies, we need to find a way of coming up with another linearly independent solution. So there's our eigenvalue, here's our eigenvector associated with that eigenvalue, and here is our one solution, okay, for our equation. Okay, so we have to find another one. Well, here's the trick. It's very similar to what we did in earlier chapters, right? We're going to take a trial solution, and we're going to look for something of this form. Yeah, so we can throw a t in there, and now we have v1 is the v1 that I have earlier. I already know that. And then we have this plus v2. So we're on v1 t plus v2 e to the 5t. Notice I'm finding a solution with the same eigenvalue of 5. Okay, so what we do is we realize the following, that if this is going to be a solution, then what we do is we actually look at what has to happen. In other words, if you plug this x2 into the differential equation, here's the right-hand side, that's a times x2. And here's the left-hand side, here's the derivative of x2, okay, using the chain rule, product rule, I'm sorry. Okay, so what we do is we equate the coefficients. We look at what has to be happen in this situation, and what we notice is that, for example, if we look at this part and if we equate that to this, right? There's a t in there. Then we get this equation. Dividing by t times e to the 5t, we get this equation right here. And there again we get our the idea that v1 here in fact must be an eigen vector for our eigenvalue 5. Okay, but looking further at the next part, if we equate the all the stuff with just e to the 5t in it, we get this equation right here. Okay, now dividing by e to the 5t, we get this equation. Okay, and then we notice that what that means, what that leads to, is that in fact, if we need to find a v2, so that when I multiply, so that basically if I take a minus my eigen value of 5 times the identity matrix, and if I evaluate that at v2, I have to get v1. Okay, so that's sort of how this technique arises. Notice here in the next part that if we have that we need v1 to be in the sort of, we would say, the image of v2. Okay, then we are arriving at this sort of thing they call the algorithm at on page where is that? For the on page 397. That is, watch this. From here, if we know this is the case, then if I evaluate both sides on the matrix a minus 5i, I get my equation right here, that in fact v2 has to satisfy the fact that when we take the square of the a minus lambda I and evaluate at v2, we need to get 0. So here what I'm doing is I'm actually going to find the square of a minus 5i. Doing that, we notice that we just get the 0 matrix in this one example. Okay? So in fact, any vector would work. And then in the next part, what I'm doing is I'm just saying, okay, I need some vector, v2, so that when I, basically, this is my equation up here, that if I take a minus 5i, v2, I need v1. And that's the equation I wrote down right here. Okay. Then observing, just sort of looking at it, you see that one solution, I can pick v2 to be just the vector 0, 1. And you see that that works. Okay. So this leads to the equation, or I should say, this leads to our second solution, v2, which I've written here, is you take v1 times t plus v2, all right, all times e to the 5t. unraveling this to find out my solutions, we have that our solutions are given here. That we have x1 is the c1 e to the 5t, c2 times t e to the 5t, and then x, so 2 is in fact um, minus 2c1 e to the 5 2 minus 2c2 t e to the 5 2, etc., etc. Okay. Now notice this is another general solution. Okay, because I have two linearly independent solutions now. Now let me do something here. I want to now do the second part of this, where I look at the get my computer system up here, and what I use is something called Grapher. You may have your own preference, but here we go. So I entered that in here, and here's what's going on. You can see the direction field here. These vectors are telling us essentially which way the solution curves would go in my space. This is my space x1, x2, or in this case it's denoted by xy. Okay, so so what do we have here? There it is, and you notice what's happening. We have this one direction. Everything is sort of either going to in the positive outward. It's expanding away from zero. Towards the eigenvector. If you look in here, you see this direction, this sort of straight off direction. This corresponds to our eigen vector. So I hope that this helps you. I will put up another video soon for you. Thank you very much.